can be an electrolytic cell, which is the kind we're going to look at next week, okay? And what is a galvanic cell? What does a galvanic cell do? What does it do for us? It can light light bulbs. It can power your cell phone. Yes? What are galvanic cells? They are batteries. Yes? So a galvanic cell is essentially a, oh, is this one not working? Oh, that makes me sad. Okay. A galvanic cell is essentially a battery. Yes? And the only thing with a battery is we've taken the beakers, which would be really awkward. Hello, you're here for AP? Excellent. Okay. So the nice thing about a battery is it is spontaneous. Okay, so it will give us energy, whereas the electrolytic cells that we will do next week are non-spontaneous. So that's like when you recharge your battery, you are doing the electrolysis process. So you're going backwards. Okay, so that's for next week. In a galvanic cell, the electrons flow through the wire from the anode to the cathode because there is a difference in potential energy. The valence electrons will be more stable in one of the electrodes than they will in the other electrode. Could you guys hit the door on your way out? Thank you. So for example, in the zinc copper system that we see so frequently, the valence electrons that are in the zinc metal are at a higher potential. So in zinc, those valence electrons are at a higher potential than the valence electrons in copper. And for you AP types, which all of you are, this is because of the shielding of the s electrons of zinc by the electrons in the filled d orbitals. What does that mean? Shall we draw an electron configuration for zinc? Shall we? Let's do an electron configuration for zinc. So I'm just going to go off to the side here. You can write it on some other piece of paper or whatever. So we have zinc. And zinc is, actually, I'm going to do this on our periodic table, because here is zinc. Do we remember how to do electron configurations at all? Do we remember anything about the S block and the P block? Where would we find the S block? I know it's been a year. The S block is here. How do I know that's the S block? Well, that's what it is. However, it's also the S block because how many electrons can fit in an S orbital? 2. And how many S orbitals are there at any given energy level? Like in energy level number 1, how many S orbitals are there? You're right. There's just 1. And at energy level 2, how many S orbitals? Just 1. And at energy level 3, just 1. The reason for that is that what shape is an S orbital? It is a sphere. Oh, look at that. And you guys who just came in, you can come grab one of these. we're getting off track a little bit. We were going to do cell potential, but we're digressing into reminding ourselves about electron configurations. Okay. S orbitals are spheres. How many different orientations can a sphere have? None. Like, it's just the one directionality, yes? So you can only fit 2 electrons into an s orbital, and there's no more because there's no other orientations, yes? P orbitals. What shape is a p orbital? This one is the figure 8 kind of it's the dumbbell shape, okay? Or I like to say it's the peanut shape. And I like peanut because it starts with a P, okay? Now, this has directionality. Unlike a sphere, which is the same from all the dimensions, this one would be in the y direction, yes? This one would be in the, well, I think I'm getting my 3-dimensional axes wrong, but that's okay, it doesn't matter. They're all orthogonal to each other anyway. We would have one in the x direction, and we would have one in the z direction, which would look like it was coming out of the board at you, yes? Out of the wall. So there's 3 different p orbitals, 3 different orientations, right? That's why we have 3 of them. How many can each orbital hold in terms of electrons? Each orbital. In total it's 6, but how many for each orbital? 2. So in total we can hold 6. So where is our p block on our periodic table? Where are we filling the p orbitals? Remember, the s orbital can hold 2 electrons. So this is going to be 1s containing 1 electron. Helium will be 1s containing 2 electrons. So far, so good? And then we'll have the 2s orbital containing 1 electron and the 2s orbital containing 2 electrons. Once we have filled up the 2s orbital, what do we start filling up? The 2p, and your 2p's are over here, yes? So those are our 2p's. So you'll have 2p1, 2p, now we have 2 electrons in there. We have 2p3, 2p4, 2p5, and this one would be 2p6. Is this ringing bells? A little bit? It's like, I do remember having seen this before in my life. Okay, hopefully. And so we would then have this little section right here would be the 3s, and then these ones would be the 3p, yes? And this whole section over here is called the p block, because when we're in that section, we're busy filling up the p subshell. What's this business in the middle? You remember? What kind of orbitals are we filling in here? It goes S, and then P, and then D. Yes. So that's the D block. And if you have trouble remembering the order they go in, it's S, P, D. Do you guys remember the last one? F, because speed is fast. Yes? S, P, D, F. Speed is fast. So we have the D block. Now, do you guys remember what happens with our D block? If all was well, we would go 3p, and then here we would have our 4s, And if life was good to us, these would now be the 4D, but they're not. What are they? This is our 3D. Yes? Okay, and then we would have our 4D down here, and then our 5D, and then our 6D. Yeah? Where do we find the F block? Down at the very bottom. Okay, so we've got that down there. That's our F block. And is this going to be, it's going to come in right here. Okay. What number will our F start with? Starts with 4. Okay, so this is our 4F, and then our, did I get that right? Yeah, 4F and then 5F. So if you want to do an electron configuration using your periodic table, let's do zinc to start with here. So here is zinc. Okay, you look here and you say, I've got my 1s and my 1s is full. Yeah? If my 1s is full, I write 1s2 because 2 is full. Yeah? What comes after 1s? I've got my 1s and now I've got my 2s. So I have 2s2. And now I carry on across the periodic table. What am I filling up now? 2p. And it's full, so how many? 6. And if you forget, you can count them. You can go 1, 2, 3, 4, 5, 6. Isn't that lovely? Yes? 2p, 6. What comes after 2p? 3s. 3s is all full. And then we fill up our 3p. How many in the 3p? 3p, 6. And then we have our 4s, 2. And then the only thing you need to remember when you start the D's is that it's not 4, it is 3. So 3D, and we're going to count over to zinc. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many d orbitals must there be? How many different ones? 5, each of which can contain 2 electrons. So we have 3d, 10. So there is zinc. If we didn't want to write out the entire electron configuration, what would we do instead? We can use the previous noble gas. So if we go back to our previous noble gas, which is argon, yes, we could write it as argon, and then we would have, oh, after argon, we would be in our 4s, yes? So it would be 4s2, 3d, 10. Yes? That's one way of writing the electron configuration. You will also see the electron configuration written this way, where we write them in terms of the principal energy level. So rather than in order of filling, we write them in order of principal energy level. Casey, yes? Pardon me? Because noble gas means that row is full, and then we're just filling the next row after that, yeah? So we have argon, we can write it this way, 3d10, 4s2. Energy level 3 electrons. So if we imagine we've got our nucleus here, and we have energy level 1, which kind of takes up this area. So that's n equals 1. And then we have n equals 2. That kind of takes up that area. We're ignoring the shapes right now, okay? We're just kind of going back to Bohr. energy level 3. The furthest from the nucleus is what? Energy level 4. Yes? You with me? Okay. The electrons in the inner orbitals, the core electrons. Do we remember that term, the core electrons? Core electrons, which are those not in the valence shell, shield the valence electrons from feeling the full force of the nucleus. Do you guys remember what we call it when we sort of take the nuclear charge and then we say, okay, there's the power of the nuclear charge, but then we take away the number of core electrons? You remember doing that? Sorry? That's ZEF. You guys remember what ZEF stands for? Effective. And what's the Z? Nuclear charge. I really need to go back. My very, very first year, I made people teaching AP, I made people do like little presentations on all of the periodic trends. And the people who did effective nuclear charge, you guys know the song American Pie? Bye, bye, Miss American Pie. Do you know that one? Okay, people. Okay. Well, they sang a whole song about nuclear charge. Charge, charge, effective nuclear charge. And then they said something else, and then it's Z minus S, right? So you have Z, which is the nuclear charge, minus S, which is the number of shielding electrons, number of core electrons. Yes? And we just look at those in terms of the main energy levels, the principal energy levels. We don't get into like looking at subshells and stuff like that. This is an approximation only. But what we can do from this is we can look and say, here is zinc. And zinc has this entire, this is zinc here, this entire D subshell shielding its 4s electrons, yes? Whereas if we look at copper, which would be argon 4s, okay, this is an exception to the rule, 4s2, 3d9. You guys don't need, you're not responsible for this exception to the rule, which would be then argon, yeah, 3d9, 4s2. Can you just believe me? Normally it would be 3d10, 4s1, yes? Did I do that right? What am I doing? What am I even talking about? What is wrong with me? No. Never mind. Sorry, I've gotten my head all tangled. Let's just pretend I didn't do that, shall we? Okay, and I'm gonna go eat lunch after this, so my brain is now functioning on food rather than no food. Okay, so we're gonna go back. That's just been our little review there, okay, of how you write electron configurations. And we're going to now go back to here because we are really still in Unit 5 which is to do with potentials. So zinc's valence electrons have a higher potential because there is more shielding. Okay? Can you just believe me on that? All right. Hence, the electrons like to flow spontaneously from the zinc to the Cu2+. So you can see up here we've got electrons in zinc. What's it going to do? It is going to flow spontaneously down into the copper. Yes? Okay. Every different substance has its own potential energy for the electrons. Cobalt is less different than zinc. Cobalt is closer in potential to zinc. So would we get as strong of a battery? No. So our voltage will be smaller. So the potential difference for these two is 1.10 volts, and the potential difference here is only 0.51 volts. So far, so good. You do not need to memorize any of these potential differences because you get your chart, which is on the last page of your data booklet. So basically, the potential of the electrons depends upon three different things. We've already looked and said it depends on what species it is. Yes, cobalt is different from copper, is different from zinc, but it also depends upon the concentration of the substance, or if it happens to be a gas, that would be the pressure. Yes? And the potential also depends upon the temperature. We'll look a little bit at how those change the voltages later, but for now, we want to make all the temperatures and concentrations the same. Because otherwise, how could you compare one half cell to another half cell if you had all different kinds of concentrations and that was changing your voltage? Yes? So on page 8 of your data booklet, what you'll see is that at the top, here we are, all ion concentrations are 1 molar in water at 25 degrees Celsius. Those are the standard temperature and concentration that we use for the half cells. So if you are asked to build or show like a drawing of an electrochemical cell, what molarity should you choose for your solution? 1 molar, okay? And what if we had a gas? Like let's say we had some Cl2 gas. That's going to be 1 atmosphere of pressure. Okay, so they're pretty easy to remember. 25 degrees Celsius is apparently like room temperature, although that's really hotter than I would like to keep my room, but you know, yes. It is an open system, but at the same, what you're doing is, we'll take a look at gas cells later on, and it's actually pumped in through a little doohickey, and we'll look at it later. Is that okay? Okay, good stuff. Where did we get to? Here we are. Come on. There we are. Okay, so this one you need to know 1 molar, 1 atmosphere, temperature is 25 degrees Celsius. And when we have those standard conditions, instead of saying E of the cell, E stands for the, is it electromotive force or something like that, the EMF? I don't know. Anyway, doesn't matter. This is the cell potential. I think the E comes from physics. Okay. What we add to that is we add the little degree sign, except for it's not called a degree sign. That little sign right there, it stands for the word not. but not like NOT, not like NOUGHT, which means nothing. Literally, it means nothing. It's not that it doesn't mean anything, it means nothing, okay? Except that we're not using it to mean nothing in this case. It's just the symbol that we use to mean it's at standard conditions. So was that confusing enough for you? It just means it's at standard conditions, okay? So you can, and you should know that it's pronounced not, so you can say E-naught cell. So you don't sound like you don't know how to pronounce it, okay? Measuring our standard electrode potentials. It is impossible to measure the potential of a single half cell. Do you remember using voltmeters in grade 9? Or maybe you've done some in physics? How many places did you have to connect your voltmeter? You had to connect it in 2 places because you were always measuring a potential difference, right? It's really, all potential energy things are about a difference. I can say, oh, this is higher potential energy, that's lower potential energy. Can I say that this is 0? I could make this 0, in which case anything below this would be negative. Or I could make the ground 0, in which case everything above the ground would be positive, and I'd have to dig a hole for it to be negative. So we're always measuring relative potentials, like between the distance between here and here is the same whether I set this as 0 or whether I set the ground as 0. So this is just a little review of the line notation for a cell. Do you remember seeing this earlier? Okay. Sometimes they call this the ion sandwich because in the middle of the sandwich there are the ions in the ion sandwich. And the stuff on the left is always the anode and the stuff on the right is always the cathode. And if you think about the half cell reactions, if this were our cell, the half cell reactions would be Cu goes to Cu 2 plus 2 electrons, yeah? And the other half cell would be Ag plus an electron gives us Ag. So those would be our half cell reactions. So that's how you read one of those diagrams, okay? What's happening to the copper? It's being oxidized. It lost electrons, so it's oxidized. Silver gained electrons, so it's been reduced. So we can play a few little games with this, and you know, I'll have some more for you next week. I didn't manage to get more together today. If we know that the potential of a cell that involves zinc and copper is 1.10 volts, and if we know that zinc and cobalt is 0.51 volts, can we figure out the potential of a cobalt copper cell? Can anyone just do it intuitively? I'm curious to see. I don't think I could do it intuitively. I have to think through it. We'll come back to this. How does that sound? Or do you want to try it now? You can try it. Don't use your table, though. I think it'll be easier if we come back to it, though. Can we come back to it? We'll come back to it, and then I'll let you try it. So how do we normally calculate a cell potential using our table and not using other data? You can use the table of reduction potentials, Or very often in the AP exam, they will simply give you the two values for the reduction potentials. Okay, and the formula that we use is that the E naught of the cell, the standard cell potential, is equal to the reduction potential at the cathode minus the reduction potential of the anode. Okay? So for example, in our zinc copper cell, if we look at copper, actually no, there's an example later on. There is another way to do it if you prefer. This is the one I like to use, but both of them are perfectly good, and both of them make, like, one of them makes more, we're out of time. Okay, we're out of time. So we didn't get through this, so my backup plan, if we didn't get through that, is for homework this week, you guys are going to do some gases multiple choice. Okay, reviewing gases, yep, and we'll finish this up next week.